Hello everyone. So in this video, we are going to continue working with orthogonal bases and finding best approximations for vectors in Rn that sit in some subspace of Rn. So let's kind of review a couple of facts that we've been discussing so far. So the first thing is, well, why is it nice to have an orthogonal basis for a subspace? Well, what makes it nice is that this finding the projection of y onto a subspace W becomes much easier when we work with an orthogonal basis for W, in that we get a nice formula for finding the weights that we need to combine the basis vectors, the orthogonal basis vectors, to find this projection of y in onto the subspace W. So namely those weights, Ci, we get by taking the vector y inner product with ui, and then we divide that by the inner product of ui with ui. And so in the case where, moreover, the basis that we have for w is orthogonal and all of the vectors in that basis are unit vectors, then these denominators all become 1 and the formula becomes even simpler. And we've also seen that we can avoid finding these weights by instead computing the product of the matrices U on the left with U transpose on the right, where U is the matrix that we form whose column vectors consist of U1, U2 up to UP, where now we're assuming these vectors are all orthogonal to each other and each of them has a unit length. So now in that case, when we have an orthonormal basis, the projection of y onto the subspace W, we can compute by taking U multiplied on the right by U transpose, multiplying that by the vector y. And the motivation for why we're doing this in part is because let's consider, for example, if W was some subspace, was a model that I have in Rn, and I would like to find the best approximation that my model is going to give y hat that sits in this subspace W for some vector y which might sit outside of our subspace. So the projection of y onto this subspace, that is going to be the best approximation. So let's consider an example for, let's say we have a subspace W which is spanned by two vectors x1 and x2 in R3, where x1 is the column vector 3, 6, 0, and x2 is the column vector 1, 2, 2. And maybe I'm given some third vector y, and I would like to find the projection of y onto this subspace W. Well, I'm not able to use either of these nice shortcuts up top until this basis that I have for this subspace is orthogonal. And here we can check that taking the inner product of U1 and U2, that gives me 3 plus 12 plus 0. I get 15, which is non-zero. So this is not an orthogonal basis for W. Most of the time, we're initially given a basis which is not orthogonal. So what I want to talk about next is a process for, given any basis for a subspace, how can we find an orthogonal basis for that same subspace? So let's take a look at an example on the next slide.